Any minute. There we go. All right, so for this warm-up, right, we have a function that tells us the position of a particle as it moves along a line, right? It's moving along a line. Now, we know this function itself is a parabola, right? But it's not moving along the parabola. I know that's hard to think. But all it's doing is just going straight, right? Or going backwards. It's moving in one direction, right? And it's given by this function right here. So to find the position, right, at t equals 3, we just plug in 3, right? The position, all we have to do is plug in t equals 3. So we have here the position function, and we're looking for it at time equals to 3. So that's going to be 3 squared minus 5 times 3 minus 8. And this, of course, gives me 9 minus, what is that, 15? Minus 8. So this gives me a negative 14. And if you really wanted to, since they don't give us or provide us with any units, we could just write down this is negative 14 units, whatever the units may be, right? If they never ask or they never tell, you don't really have to put down units. But if they ask for units, the default one is just units. But if they put down feet, then you got to put down feet. If they put down meters, you got to put down meters. If they ask for the units, and that's actually a key thing when you're dealing with calc problems. They won't ask you all the time for the units, and if they don't ask you, you just leave it out. Because if they don't ask for it, but you put the wrong units, they take a point off. If they don't ask for it and you don't put any units, you get the full credit. I know that sounds weird. And you still get the full credit even if you put the right units. So it's kind of like, only put it there if they ask for it. If you're taking AP Physics, on the other hand, always include your units. Even if they don't ask for it, make sure you're checking your units as you go. Okay? I know that sounds like, which one should you do then? Traditionally, if you want, pay attention to the units. That's pretty much all I can say. Okay? Pay attention to your units. All right, that's for position. For velocity, right? You guys remember that the derivative of the position function is equal to the velocity function, right? The velocity at a specific point, the instantaneous velocity, I should say, is equal to the derivative, not the average velocity, right? You still are going to be in charge of finding average velocity and instantaneous velocity. Those are two separate things, and you need to get that in your mind, right? Instantaneous velocity at a specific time is the derivative. Average velocity is over a amount of time from one point to another, right? Like if I was doing the average time from t equals 3 to t equals 4, I want the average speed there, not the average time, right? Whereas I want the velocity exactly at t equals 3, then I need to take the derivative of this. So taking the derivative of the position function, I get my velocity function, which is going to give me 2t minus 5. And hopefully you guys understand, right? All I'm doing is looking at this original position function, and I'm taking the derivative with respect to time, right? With respect to time. Because that's what velocity is. It's the change in position over the change in time. And that's what I'm doing here, taking the derivative of position with respect to time. Anyways, I'm talking too much here. Let's go ahead and take a look at what is the velocity at t equals to 3. We simply just do the same thing we did with the position function. We just plug in 3. All right, so I plug in 3 right here. I'll get 2 times 3 minus 5, and you end up with 6 minus 5. I'm not even going to write that down. That's just going to be 1. Now, if you're looking at the units for this one, this is 1. Thank you, Brian, for asking, by the way, what is the units for this one? For time, there's no default one, I guess, but this one I'm just going to call it for seconds, so it's going to be 1 unit per second if you wanted to write down the units for this one, right? Foot per second, feet per second, meters per second. It could be meters per minute. Just pay attention to the units, like I said. But again, if it didn't specify to write down the units, you wouldn't get marked off if you just left it as 1. You wouldn't get marked off if you just left it as 14, right? I did not specify the units. You don't have to write down the units, okay? That's the velocity function, okay? Last one is the acceleration. The acceleration function. And again, this is now comparing how fast is your velocity changing with relation to time, right? So velocity was how fast is your position changing in relation to time. Acceleration is how fast your velocity is changing with relation to time. That means that acceleration, right, is simply your velocity function, but it's derivative, right? So you're going to take the derivative of the velocity function, or in other words, the second derivative, right? And you're allowed to do that. You can take derivatives more than once, right? You can take the derivative once and then take the derivative again, and that's the second derivative. If you want to write it out, by the way, notation-wise, it's the first position function taking the derivative twice, and it would just write that prime twice. I don't know if you guys can figure this out, but can you guys guess what the third derivative would be written as? What's the symbol for that? And you guys will see it in a second. Or you guys can guess, what do you think the third derivative will look like if you take another derivative? Anyways, the derivative of 2t minus 5 is simply just going to come out to be 2. It's a constant function. This thing has a constant acceleration, right? That's all this is saying. And that means that at time equals to 3, the acceleration is still 2. No matter what time is, the acceleration is always 2. That means this thing is always going to be accelerating. It's always going to be going forward no matter what it was doing before. It's always accelerating towards one direction. Right? It doesn't change at any point. Right? So that's the connection between all three of these guys, right? If you have a position function, the derivative of the position function is the velocity, and the derivative of the velocity function is acceleration. Right? So whatever relations you have, whatever functions you have that are relations of one thing to another, you can always take the derivative of it and find the rate at which it's changing at a specific time, right? And it doesn't just work for position. It also works for like area, for example. You guys understand that the area of a circle is in relation to its radius, right? Or its diameter, however you want to define it, right? And if you have a circle that's increasing its radius a certain amount, the area also increases a certain amount. You can always compare that as well. And it's up to you what you need to, it's up to the problem what you need to compare. But I'm starting you off with a basic idea of how calculus started, and it had to deal with position, velocity, and acceleration, right? Anyone figure out, by the way, how to do the third derivative? How do you write the third derivative? What does that notation look like? If the second derivative has these little 2 tick marks here, what do you think the third derivative looks like? Any idea? Yeah, just 3 lines, Max. That's it. 3 lines. 1, 2, 3. The third derivative with respect to time, right? Anyone have a guess, by the way? What's the name for when you're looking at the comparison of the change in acceleration over the change in time, right? If the first derivative of position is velocity, the second derivative of position is acceleration. Anyone have any idea what the third derivative of position is? I had to look this one up. No, it's not a free fall. It's not a free fall. How fast an acceleration changes over time actually has a name. We looked this up last year because I had no idea what it was. So I didn't know it. Does anyone else know it? I'll tell you what it is if you want, but maybe some of you guys do know it. Anyone? Want to take a guess? We looked it up, and it's called a jerk. It's called a jerk. A weird phrase, right? It's called a jerk. The third derivative of a function, of the position function, is called a jerk. What is that? Oh, it's a jerk. You're a jerk. All right. Anyways, so if you're ever asked, hey, what's the jerk at a specific time? Just take the third derivative of the position function, and you'll be able to take a look at that. So that's pretty much the idea behind like these different rate problems, right? You can, all a rate problem is just comparing what it is you're measuring divided by, it's like what's in your y-axis divided by the change in your x-axis, which is the slope, right? Which is what we've been doing this whole time. But if you want a slope at a specific point, that's called the slope of the tangent line, right? Because it's only touching at that one point. And that, of course, leads us to what we've been learning this whole time, which is the derivative, why we've been needing to learn these derivatives. Okay? So that's that one right there, guys. Let's move on to today's stuff. I wanted to continue here. There is some terminology that I wanted to talk to you guys about, right? You plug in the number into this thing, it tells you the position of your object at a specific time, right? You plug it into its derivative, that tells you the velocity at a specific time, and you plug it into its second derivative, it tells you its acceleration at a specific time. There is a few things that I wanted to talk about real quick, which is terminology. So real quick here, let's say I have a particle, right? And it starts right here, right? And this is its initial starting point. So at this point right here, I'm going to say how far has this thing traveled at time equals 0, and it's traveled none, right? Its position is right here, and this is the initial starting point right here. And then it decides to go this far and end at this point right here. It's traveled over here a distance of, let's say, 5 feet, right? It's traveled a total distance of 5 feet. So right here, and he did this in, let's say, 2 seconds. So in, that's really long. Let's say 1 second. So in 1 second, this guy traveled 5 feet. Right? Now, here's the thing. The position that he's at, right, after 1 second is 5 feet, and the total distance he's traveled is 5 feet, and his displacement, that's the new word I wanted you to talk to you guys about. Displacement is also 5 feet, right? So most of the times it's pretty straightforward, and we don't really talk much more about it because it's always the same concept, the same idea. But displacement is not always going to equal to where your position is, right? Displacement is not always going to equal to where your position is. Displacement is measuring how far away you are from when you started, right? So what if the same person who started right here, right? Same thing, S of 0, right, is at 0 feet, right? But this time, this person decided to walk, he decided to walk up this way 3 feet, right? And then decided to walk this way 4 feet, right? Let's draw that a little bit better, down to here, right? And he ended up over here at this dot right here. Okay? This person, here's the thing. How far has this person traveled, right? How far has this person traveled? Can you be able to tell me what's the total distance this person traveled? 7 feet. Good. No trick questions here. Total distance traveled, right, is 7 feet. But here's the thing, though, right? You got to be careful for these questions. They'll ask you things like this, and you'll know what the total distance is, or sometimes you will have to do a little bit more work to calculate it. But make sure you understand, though, the displacement right here is not 7 feet, right? What would the displacement be looking like right here? The displacement. Wow, did I spell displacement wrong? Is it E-M-E-N-T? Or is it without the E? I forget. The displacement is still this guy right here, right? How far away is he from the beginning? And if I told you that this right here is 5 feet, right? I'm hoping you guys will see that the displacement right here is 5 feet, right? Yeah, that's it, Jeffrey. So displacement isn't measuring like how far something's traveled. It's just measuring how far away it is from this point to this point. I don't care if it's done like all these random things, right? It's just from here to here. And that's one of the tricky parts of these problems. It's a lot to remember, right? Velocity is derivative of position and all that stuff. And then you can figure all this out. But the displacement is just the measurement how far away it is from it is that you're initially looking at. Not from the origin, but just from where it is, whatever the 2 points are that you're measuring, right? So give me a second here. Let's take a look at this problem. No, not that one. Let's take a look at this problem right over here. It's the same one as before, but this time let's take a look at calculating the displacement, right? Let's calculate the displacement. So let's go ahead. I'm going to move your Pear Deck over to the next slide. Just give me 1 second here. Where are you, Pear Deck? There you are. So let's take a look at the same function, right? The same function. It's the particle that moves along the line by this function here. But let's calculate what's the displacement from t equals 1 to t equals 7. Let me put that on the screen real quick here. So I already have it on your Pear Deck. You guys can go ahead and try it out if you want, or you can follow along with me as I explain it. Here is the same problem we were looking at earlier, except now we're not looking at velocity or acceleration, right? We're going to look at its displacement from t equals 1 to t equals 7, right? From t equals 1 to t equals 7. And what is its displacement? Now, remember, the displacement is the difference in the position, right? It's the difference in its position. So I need to figure out, first of all, what is its position at t equals 1, right? And how do you find out what its position at t equals 1? What do? You just plug it in, right? So the position at t equals 1 will be 1 squared minus 5 times 1 minus 8, right? So the position at t equals 1 is equal to, it looks like 1 minus 5 minus 8, which is going to give me, what is that? 1 minus 5 minus 8. Negative 12? Negative 12, right? So the position of this guy, right, is located at negative 12 after 1 second, right? That's what this is saying. What's his displacement? Well, then I got to figure out how far does he travel, right? Or where does he end up after 7 seconds? So I do the same thing. I do the position function, but I plug in 7. So I have here, this is going to be 7 squared minus 5 times 7 minus 8. All right, do this calculation real quick. S of 7 is going to give me 49 minus 35 minus 8, which tells me this particle's position after 7 seconds. His position will be at 6 feet. Right, so what's the displacement here? What's the displacement? What do you think? So that's the part that gets a little bit difficult for these types of problems right here, right? So remember, this particle is moving along a line. So here's my line, right? And here's 0 just to help me reference it. At 1 second, at t equals 1, this particle is standing at negative 12 feet. So it's over here. Here's negative 12 feet. Here's where my particle is. After 7 seconds, he's standing over here at 6 feet, right? When I'm asking for the displacement, I'm just asking for this distance from here to here. I'm not asking how far he traveled, right? I'm not asking the total distance that he's traveled. I'm just asking, right, what's the displacement? And you just simply subtract the two, right? The displacement for this problem man, I'm having trouble spelling today. The displacement is simply going to be equal to negative 12, right? Actually, I'm going to do it the other way. I'm going to do 6 where he finishes minus from where he starts. That actually is easier, right? It's not always positive. It's not always positive. In this case, I made it positive, though, because I didn't say I make it positive. In this case, it is positive is because he's going from negative to positive, right? When you're doing displacement, you're always doing where does he finish minus where does he start, right? It'll be the finish minus the start point. That's the easiest way to do position, right? So it's 6 minus negative 12, right? Which tells me that the displacement that this thing has is 18 feet. That's what the displacement is. Okay, that's the displacement. And these questions, you got to be careful with that. But how do we get 5 in the other example? How do we get 5? Oh, I just made this one up. This 5 is not the same S, Max. That's a different S. Sorry. This was a side problem. This had nothing to do with that. So I was just drawing one just to emphasize the fact that, like, if you draw these other lines out, displacement, it doesn't care that you go in all these weird ways. It just cares about where you're starting and where you're finishing, right? But there will be times where we care about how much does it travel in between and all that stuff. But for right now, we just cared about the displacement at the end. Okay? All right. Okay. You guys feeling okay with this? Hopefully you are. I wanted to go over one homework question with you guys. That was hopefully that you have looked at your homework. But if not, we'll go over it together right now. There is where's my mouse? There you are. There was one homework problem that a lot of students were asking me about, so I kind of wanted to go over it in class, just because it was a it was a tough one apparently. Let me see here. Where are you? AB Unit 2. Do I not have your homework in here? Uh-oh. Where did I save your homework? Shoot. I did not save your homework in the right spot. Give me 1 second. You know what? Why am I doing it that way? Well, let's just go to your let's just go to the actual homework page, right? Duh, knock me. Duh. Hello. Let's go over here. Let's take a look at this one problem I wanted to share with you guys. which is from the 2.4 to 2.5 homework. Right. Oh, by the way, there's 2 pages on here, so 2 sets that you need to do. One from this page, which are these problems, and then the other one from this page. All right, so be careful with that. Make sure you are doing them all. I tried to add the writings onto the actual pages themselves as well. So if you actually see here, for the first page, it tells you to do 23, 24, 26, 28, 29, right? Let's see, 23 would be like this one down here. People were asking about this one. We'll do more practice with this right here, but this is like basically calculating the derivatives using a table. But you should know that if you have a function u and a function v, you need to do the product rule, but that's not the one I want to talk about. So that's just more practice with derivatives. But this is the one I want to talk about, which was right over here, which was these types of word problems, right? They're not actual word problems. They're not actually that crazy, but they look weird, right? They look weird. So I wanted to talk about this one, for example, right here, number 2. Let me go ahead and copy this guy. Right, so it takes a little bit of practice, but this one right here was easier to do because you're looking at position, right? And they just tell you this is the position function, and if you take the derivative of the position function, you end up with velocity, and right, velocity compares position to time. Well, this one right here, did I not copy that? Oh, I did. It's up here. Come on. Come on. Come on, buddy. Anytime now. That's the slowest scroll ever. Let's go. There we go. Okay, so let's take a look at this problem right here. This is from the homework, so you guys might want to copy it down just to help you guys out. When I'm talking about rates, right, it doesn't necessarily have to be position compared to time. That's just an easiest rate to talk about because we deal with that all the time, right? Like, if you're driving your car, you're changing by miles per hour, right? And that happens very often. You're riding your bike, you're going by feet per minute, right? Or if you're running, right? Depending on how fast you run, how fast you're going, feet per second or feet per minute as well. This book will take this and make it very abstract and start looking at rates for really different things. And in this particular case, it's looking at a rate at which an area is changing compared to its circumference, right? So before you can actually do that, you have to write an equation for it, right? So what they're saying is if the circle is this big, right, you can calculate its area. And traditionally, we calculate its area using pi r squared. And this is also a rate, by the way. You can compare, right? If you take the derivative of this with respect to r, right, you'll get this guy. By the way, if you take the derivative with respect to r, the notation is this. dA over dr, which represents the change in area over the change in the radius, right? And that's going to be equal to pi times 2r, right? So ignore that question up there. Just have a look here. And this is what I wanted to show you here, is when we dealt with position and time, right, it was feet per second. With area over its radius, right, if let's say the radius was measured in feet, let's say, right? The radius is measured in feet. So let's say this right here is like 5 feet, for example. The area would be equal to 25 pi feet squared, right? If the radius was 5 feet. So when you measure these guys, when you're measuring the rate of change of this guy, right, the unit you'll get for this will come out in feet squared, because that's what the area measures, per feet. And this is like, I don't know, when I learned it, it was really weird to me. It was like, what? But all it is, if you think about it slowly, is, right, if you think about it carefully, I shouldn't say slowly, if you think about this carefully, is you're looking at the rate at which the area is changing compared to the rate at which the radius is changing, right? So that's that in a nutshell. So when you do these problems, don't let this one trip you up when you're talking about these different things. The only thing is this one doesn't ask for the area as a function of the radius. It's asking for a function of circumference. And this is where, like, I'm telling you, the algebra part is the part that messed up a lot of students for this one right here. So let's see here. Let's take a look at this real quick. This is an area of a circle as a function of its radius. But if you replace out the radius part with the circumference, which is circumference is 2 pi r, if you are able to switch it out you can then rewrite this as a function of the circumference. So in order to do that, you have to solve for r and then replace it in there. So just a little bit of algebra here. Circumference over 2 pi is equal to r. And what you can do is replace the r with this right here. And you'll have area is equal to pi times circumference divided by 2 pi. And that's your area function as a function of the circumference. Anyways, that was that problem in a nutshell. I just wanted to show you guys, like, don't get tripped up by this part right here. That's not the calculus part. That's literally the algebra part. The calculus part is you finding the instantaneous rate of change, which is a key word, by the way, for you to take the derivative. Okay? So when you get into these problems, don't get tripped up by the algebra. That is important, by the way, on you setting up the equation. But the calculus part is you doing the derivative of that, and you need to practice taking derivatives of these guys right here. Oh, sorry. Squared. Almost messed that up. But yeah, so just a heads up. I just want to give you that heads up when you guys are doing that homework assignment, which, by the way, you should get on that. Get on that homework assignment. I think we're almost done with this chapter, so that means most of your homework will be due soon, I believe. Soon. I want to give you this heads up right now. I think your test is going to be next week. I think your test is going to be next week. I haven't figured out on the day yet. I need to get you guys your review and all that and see how far we can get in today's lesson and see where we can finish in today's lesson. All right, I'm going to close my OneNote and reopen it because it is lagging like crazy, and I don't know why. Give me 1 second. Bring that back over here and go over onto today's notes. You guys are period 3, and here we go. So that's the small talk I wanted to talk to you guys about the homework. Okay? All right, let's move on. Okay, let's move on. We're going to go over to this new lesson today, and it is basically derivatives, but when you don't actually have the function, but you have table values of the functions. So let me go ahead and show you what that looks like. So if you want to title today's notes, all right, let's call it 2.6 derivatives with a table, right? Derivatives with a table. Yeah, derivatives with a table. I think that's going to be everything, right? I think that's everything in this chapter, yeah. I believe so. I believe so. Oh, I hope so. Hope I didn't forget anything. All right. Let's take a look. Here we go. So derivatives with the table. Nope, that's not what I want. Alrighty, there you go. Right? Involves you knowing your rules, like you've got them down. You've been practicing your derivatives, so you know your derivative rules perfectly. Like, for example, if you just had a function, add another function, and I take the derivative, like if I had, for example, 3x to the 4th plus 5x squared, and I asked you, hey guys, can you take the derivative of this, right, with respect to x? You guys should be able to do this with no troubles, no problems, right? You have that this is the addition rule combined with the power rule, combined with the coefficient rule. But of course, you already know, like, you do this without even knowing those, stating those rules, right? You know them by heart now, because the derivative of this would be, right, 12x to the 3rd plus 10x, right? That's no question questions involved, right? Hopefully, if there is a question, can you let me know? Right? Are you still stuck on how to calculate the derivatives of a function that's like this? Let me know, and we can go over it. Okay? All right. What I'm saying is, then you wouldn't be tripped up if I told you, hey, find the derivative of f of x plus g of x, right? With respect to x, right? And you guys would be able to tell me, oh, the derivative of f of x plus g of x, well, that's just the derivative of f of x plus the derivative of g of x, right? That's all that is, because that's what you're allowed to do. But if I had, for example, f of x times g of x, and I asked you to calculate the derivative of this one, right? You guys wouldn't tell me that it's the derivative of f of x times the derivative of g of x, right? You'd be able to remember that this is the product rule, right? This is the product rule. And you have to actually take the derivative using the product rule and tell me that, oh, that's the derivative of the first function times the second function plus the derivative of the second function times the first function, right? And if this looks weird to you, it's because we don't really write out with this notation. We just write it out with the work that we have to do. So for example, right, you guys have done this already. It just looks a little bit different. But if I gave you a function, let's say it was x squared times cosine of x, and I asked you, hey, find the derivative of this guy for me, right? And you are going to need to know how to do stuff like this one, so you should be practicing this, right? The derivative of this, right, is not going to be 2x, right, times negative sine of x, right? Hopefully you guys don't write that down. 2x is the derivative of x squared, negative sine x is the derivative of cosine, but the derivative of them multiplying together is not this, right? You would apply this guy right here, right? If this is my f of x and this is my g of x, you apply the product rule, right? And you do all that work and you get, of course, 2x times cosine of x plus negative sine x, right, times x squared, right? And of course, that's coming down from this guy, right? Hopefully you guys can see it, where this is coming from, right? This is the derivative of f of x right here, right? And then this over here is this guy right here, which is just g of x. And then this over here is the derivative of g of x, right? That's where it's coming into play. Oop, like so, right? And the reason why I'm bringing this up is this is nice when the functions are just written there for you and you can see, oh, it's one function times another function doing the derivative. I know how to do the derivative of this. I know how to do the derivative of that, right? I've become a pro at it. Same thing with this guy over here. I know the derivative of this. I know the derivative of that. Super easy to do because you just follow the rules and you've seen the pattern for them, right? Sometimes on these problems, though, when they ask you to do derivatives, they don't give you the function. They tell you about the function, and then they tell you the numbers that the function spit out. Like, what are you saying, Nakmi? Let me show you, right? Let me show you. So here's an example. So function derivatives with a table. Let's start it off right here, right? Derivatives with a table. But here's a table. Okay, I'll give you guys a second to copy down this table. If you want, you can screenshot it. You could also, let me open up the Pear Deck, and you can actually take it from your Pear Deck as well. I think I have it in there as well. So yeah, go into the Pear Deck. I think, yeah, the table is in there. So if you want to screenshot it from there, you can. So you don't have to write it all down. But that is what I'm working with, right? So this is what I mean. This is a table, and it tells you there's two functions that you're working with. You're dealing with f of x and you're dealing with g of x, but they don't tell you what they equal. They don't tell you what f of x is. They just tell you, here's a function, and when you plug in 1, f of x will give you -3, but g of x will give you 2. I don't know what this function is. I don't know what these functions look like. I just know that those values that input is gonna give me that output depending if I go to f of x or if I go to g of x, right? They're hiding the function from us. They're only telling us what the output value is. They also tell us the derivatives as well, by the way. They also tell us the derivatives at that point. They tell us the slope of the tangent line at that point, okay? All right, so what the heck's going on? Let me show you. So let's say I have a third function, right? A third function, let's call it h of x. Right? H of x is going to be equal to f of x times g of x. Okay? And for this problem, they want us to find, right? They want us to find the derivative of h of x evaluated at 1. Okay? Now, how does this work? Well, they're asking us to find the derivative of h of x. Well, what's the derivative of h of x? It's this derivative right here. They want us to take the derivative of f of x times g of x, which means I have to apply the product rule. Okay? So, before I can actually do the derivative evaluated at 1, I need to find the derivative first using the product rule. So check this out. The derivative using the product rule, right? I know that it's simply the derivative of the first times the second function plus the derivative of the second function times the first, right? So if I want to evaluate this thing at 1, I simply just plug in 1 wherever there's an x. So what this is saying is then if I want the derivative of h of x evaluated at 1, it's going to be the derivative of f of x evaluated at 1 times g evaluated at 1 plus the derivative of g evaluated at 1 times f of evaluated at 1. How does this work? The table gives you all these specific values, right? Check this out. Hey, buddy, what's the derivative of f of x evaluated at 1? Why, that's simply 4. So that's what I write down. This is going to be equal to, you ready? 4, right? What's this next one? What's g of 1? G of 1 is right here. That's just 2. Plus, let's go with green here. What's the derivative of g evaluated at 1? It's equal to 7. Okay, and last but not least, what is f of 1? Why, that's just that one right there, and that's going to be -3. So, what is the derivative of the h function evaluated at 1? I just do the math. 4 times 2 is 8, plus 7 times 3, which is -21, which is going to give me -13. That's my answer. All right, I hope I did that right. Yeah. You guys okay? I know it's Monica's saying yes, Judith, yes. It's strange, but it's not too bad, right? You're just following this table, right? And you're calculating the derivative using that. Emily's saying yes? Okay, good, good, good. Let's have you guys try one. Let's have you guys try one, okay? Let's have you guys try one. Let's say I was asked to find, I was defining a function. Let's call this function, what's a good letter? Let's call it s of x, right? This function is called s of x, right? And I want you to find, s of x is defined as f of x plus g of x, right? F of x plus g of x. And what I want to find from you guys is, can you guys find the derivative evaluated at 3? Can you guys do that real quick? So the Pear Deck is open. Can you guys try this out? And again, just try it. I'm not going to grade you if it's right or wrong, because this is the first time we're doing it. But I want you to try this. See what you guys get. And you find out what is the derivative of f of x, I'm sorry, s of x, if it's defined to be f of x plus g of x. Okay? So find this for me. What is s prime evaluated at 3? Go ahead and try that. Let's go with 3 minutes. Let's see how far you get in 3 minutes. I just realized I need to set a timer, or else we'll be here forever. 3-minute timer. Try this out. Oh, that's gonna block everything, isn't it? Yeah, we'll just put it like that. While you guys are doing that, hopefully you guys are feeling all right. I was talking with coworkers yesterday. You know how like all the teachers have meetings on Mondays from like 1 to 3, so we can't hold office hours on Mondays? Everyone was discussing about like mental health stuff and how everybody's doing. And you know, to be fair, I haven't actually checked in with you guys as much, and I feel a little bad. Everyone else has said they've been checking in with their students. They said all their students have been kind of down. And I was like, oh, crap. Are you guys feeling the same way? Are you feeling a little bit down? I just haven't been giving you guys enough attention on that. In my mind, I don't know. I feel like you guys are happy to talk about math, but then that's just me living in a bubble, right? Yeah, hopefully you guys are doing all right. Talked to some of my other students in my other class, so they were saying they were playing Call of Duty. They're playing the beta for, what was it, Black Ops, the new Black Ops that's coming out soon. That sounds like fun. Cold War. Is that what it's called? It's not. Is it called Black Ops Cold War, or is it just Cold War? Yeah. Okay. Black Ops Cold War. Here's the thing. I haven't Warm War. Oh my God, David. Here's the thing. I haven't checked it out, but have they gotten rid of like the? I know that this has become like a staple now, but I stopped playing when they had this. Was when the characters can like slide, run and slide, like not dive, but like just slide or wall run. I remember that was the other one. Like you could like run across the walls. I think it was like Black Ops 3, or I hated that. They like made me not want to play it. You can still slide, but they don't do wall. But they don't wall run. Okay. If global warming is real, then why is there a Cold War? I mean, why was? I miss diving. All right. I miss diving. They took out diving, so you can't dive at all. You can't go prone. That was like my favorite. If you're capturing a point, you go and dive on the point, and then you're prone. And you just like machine gun everyone down. All right, guys. Let's take a look through the answers here. Leslie, that's a beautiful answer. Good job. Monica, good try. Jocelyn, good. Thank you for your answer. Brian, good. I like these answers. Angela's wrote down something. Juliet, that's an interesting drawing. Emily, I love the work and the colors, by the way. I love the Aurelie, that beautiful work. Beautiful answer. All right, Eric, thank you for your answer. Joe, thank you for your answer. Radhish, thank you for your answer. Brian, thank you for your answer. Gracie, beautiful colors. Thank you for your answer. Jeffrey, thank you for your answer. Max, thank you for your answer. Who else we got? Frankie, thank you for your answer. Diana, beautiful, beautiful. Shirley, nice colors. Keep up the good work. Calvin, nice. You're showing the work now, aside from actually just having the answer this there. I appreciate that. Fatima, good, good. Don't forget the tick mark. Don't forget the tick mark, because if you just write down S of 3, it looks like you're only finding the function at 3, not the derivative, right? Brandon, thank you for your answer. Ava, thank you for your answer. You're working it out still, looking good. David, what? What are you drawing, David? Also, do the colors like go light like that when you write that? All right, check this out. I'm asked to find the derivative of S. Okay? I'm asked to find the derivative of S. But I know the S function is just the F function plus the G function. So if I'm taking the derivative of this, it's the addition rule, right? It's just the derivative of F plus the derivative of G. That's it. I don't have to do the product rule. I just do that, right? And then if I'm evaluating the derivative at 3, I simply just plug in 3 into the derivative that I just found. Wow, I just wrote an X on it. I should be writing a 3, right? So what I'm noticing is, right here, let me erase these colors and start over here. I'm saying that F prime of 3, right here, is simply 7. Wait, it is 7, but that's the wrong 7 I circled. It's simply 7, right? And then what's the derivative of G evaluated at 3? Well, that's simply just 9. How do I find then the derivative of S evaluated at 3? I just take those numbers and I plug them in, right? So I have here, this is going to be equal to F prime of 3, which is going to be 7, plus G prime of 3, which is going to equal to 9. So that means that my derivative, of course, is equal to 16. And that's it. S prime evaluated at 3 is equal to 16. Okay? How's that? Not too bad, hopefully? Don't you multiply the 3? No, we do not multiply with 3. Be careful with that. 3 being plugged in is not to multiply. 3 is a number that plugs into the function. It's not multiplying with the function. Now, if s of x was equal to 3 times f of x, right? This is a side problem. If I ask you to take the derivative here, thanks to the coefficient rule, this would be 3 times f prime of x. And in this case, I would multiply by 3 if I was plugging in 3 for x, but not because of this 3. That 3 gets plugged into the function, and that 3 right there is just simply telling me where to look on the table, right? It tells me where to look on the table. So this 3 right here is not a 3 that you multiply by. This 3 is simply to tell us on the f function, or the f prime function, I should say, what's the x value to tell me where to find the output value, right? That 3 is the input value. That's all it is. David, that is not an answer to this question. That is a ocean that you're drawing? Julia, the Pac-Man. But yeah. Oh, that's where you got that answer from, Brandon. I see. Okay. I got you. But does that answer your question, Brandon? Why we don't multiply by 3? Okay. Awesome. All right. Let's try another one. Let's go with a new table. So let's go down here. Here's my new table. No, that's the same table. Knock me. Get out of here. All right, here's my new table. Let's go with this guy right here. That's what we're going to be working with. And let's see here. Am I going to ask what am I going to ask from you guys? All 3. Okay, that sounds like fun. Let's go ahead and have you guys try this. Okay, 3 functions here, or three different things I want you guys to find and evaluate at different points. So there's an A, there's a B, and there's a C. First one is the 2 functions adding together. The second one is the 2 functions multiplying with each other, and the third one is the 2 functions dividing each other. So can you apply the rules that you've learned, calculate these derivatives, and then evaluate it at the given values that you have here? All right, so try this out. I have the Pear Deck open. Answered in 3 different spots. Can you guys go ahead and try that real quick? See what you guys get. This one, I gave 3 minutes for the other one for 1 problem. There's 3 problems here. Let's go with, I'm supposed to give you 9 minutes, but I feel like that's too much. Let's go with 7 minutes and see where you guys are at after 7 minutes. I'll be taking a look at your work right here. So give me a second here. Let's go 7-minute timer. You can do the work on the Pear Deck. You can do the work on the side and then put the answers on the Pear Deck. That works as well. I just want to see where you guys are at. If you're stuck, by the way, and you need some help on how to start this, I'll start you off with this first one. All right? d dx is a fancy word for saying to take the derivative. So I'm asked to take the derivative of f of x plus g of x. Since the 2 functions are being separated by a plus sign, the derivative, I can just take the derivative of each one and add them together. Meaning, what's the derivative of f of x? Why, that's simply f prime of x. What's the derivative of g of x? Why, that's simply g prime of x. And I just add them together. And then I need to evaluate it at 4. And hopefully you guys can look at the table to figure out where those values are. And that's how I would start off that first one. All right, that's how I would start off that first one. So keep going if you already got that one. Keep going. Either or, Brian, either or. Fraction form or decimal, both are fine. Either or. Let's see. Excuse me. Looking good so far. Some answers are matching up with each other. Some answers are a little bit different. I love to see the attempt. That's what I want to see. I just want to see the attempt. That's beautiful. Okay. If you feel unsure about your work, you could always write down what it is that you plugged in, and that makes it easier for me to grade. Just a little tip if you guys ever are doing one of my tests, right? Partial credit is your friend. So when you do these free response types of questions, don't just give me the answer, because if you get it wrong, then you just don't get any points. But if you show me what you were attempting to do, I can give you partial points, right? Even if what you're attempting to do is wrong, we can actually see and take a look at what it is that it should be. Okay. So just keep working through. Looks like most of you guys are getting that first one. Except for David. Davis is drawing skies again. David, knock that off. Go do your work. That's not work. That's just drawing. Is that a just blue on green? I was like, are you trying to draw a tank that's blue? Okay. Got a nice mixture of answers, though. Some people like keeping it in fractions. Some people like putting them in as decimals. By the way, I'm missing, double checking my attendance for those who are not here. I'm missing Mark. Mark, are you here? If you're here, can you type into the chat? He ended up showing later last time, I think on Monday. And the other person I'm missing is Kimberly. Kimberly, are you here? If you're here, please type into the chat for me. All right, it's been about 7 minutes. But looks like some of you guys are still working on it. not just leaving it blank. So let's go for a couple more minutes. Oh, that's what you were drawing, David. You have time to do that instead of just working on the problem? I mean, I do appreciate your drawing. That is a nice drawing. But come on. I am like impressed by some of you guys' handwriting on here, though. Should I say mouse writing? You know what would have been cool if you're the Chrome decks. Chrome deck. What would have been cool is the Chrome pod. Oh my god. I'm combining Chromebook with Pear Deck in my mind. I don't know why. But what would have been cool is if the school gave you a Chromebook that was touchscreen. You know? If they gave you a Chromebook that was touchscreen, then that'd be awesome. And then you could just draw on the screen and you could write on it with a pen. But, c'est la vie. You have to wait until the prices of those go down and you guys will already be done. We'll be out of here when that prices go down. All right. Let's see here. The first one, right? F of x plus g of x is the function that we're working with. And I'm asking you, what's the derivative of f of x plus g of x evaluated at 4? Well, you already know that since it's a function plus another function, you can just use the sum rule, right? The derivative of f of x plus the derivative of g of x. And then just evaluate it from there, right? This is going to tell me that, oh, I'm going to be looking at it for f prime evaluated at 4 plus g prime evaluated at 4. And all I'm simply going to do is just look at the table for this, right? F prime evaluated at 4 is this fraction, negative 4 over 5, plus g prime evaluated at 4, which is negative 1/3. Right? If you got that far, that's awesome. That's beautiful. After that, then it's just a fraction work, right? Get a common denominator and add them together. Common denominator here would be 15, I would believe. So you multiply top and bottom over here by 3, and you multiply top and bottom over here by 5, right? So I get over here, this is going to give me, let's double check real quick here. This is going to give me negative 12 over 15 plus a negative 5 over 15. Did you guys get negative 17 over 15? That'd be my answer right there. Negative 17 over 15. It is reduced, and I would leave it like that. Improper fractions, I don't know why they say it like that, but I like that more than a mixed fraction. I like that it's easier to deal with if you have to plug it back into something else, because it's plugging in a mixed fraction just really annoying. But if you want to write it as a mixed fraction, it'd be 1 over 1 and 2/15 if you want it as that. And as a decimal, I'm sorry, negative 1 and 2/15. And if you want that as a decimal, I think it comes out to like 1 point. I don't got it. I can't do that in my head anymore. This is 1 point something if you want it as a decimal. So know how to do all that, know how to simplify it, right? Technically, like you are technically done here. You don't have to do that further part, but if you're doing a multiple choice test, I guarantee you it'll either look like this or it'll look like a decimal. So I'll leave that up to you. Okay. Number two, you are looking at a product rule for number 2, right? It's the derivative of the first function times the second function plus the derivative of the second function times the first function. Please understand that's what you need to do for the product rule for this one, right? So I'm not just doing the derivative of f times the derivative of g. If I did that, that would be wrong. That's not how derivatives work when your functions are being multiplied. All right, it's the derivative of the first function evaluated at 1 times the second function evaluated at 1 plus the derivative of the second function evaluated at 1 times the first function evaluated at 1. Okay, which is going to come out to be derivative of the first function evaluated at 1 is a fraction, and that looks like it's 5 over 3. The g of x evaluated at 1 is just 1, right? Plus derivative of this second function evaluated at 1 is a fraction of 2/3 times the first function evaluated at 1, and the first function evaluated at 1 is another fraction, so it's 1 over 3. So it'd be this guy right here, right? And again, if you're having trouble on seeing how I'm getting these values, right? F prime of 1 is this guy, right? G of 1 is this guy right here. G prime of 1 is this one right here. And F of 1 is this guy right here. And that's how I got these numbers right there. Okay, that's all it is. You just look at the table. But the hard part is understanding and remembering that you still need to apply the rules to do these derivatives. Anyways, I'm going to run out of time, so I want to make sure you guys get these answers. Double checking real quick. For this one, simplify, multiply, and combine like terms, you'll get 17 over 19, right? For this one over here, please make sure you do low D high minus high D low over low low. It's a quotient rule for this last one. And this last one is going to be low, but evaluated at 0, D high minus high, D low, all over low low, right? You plug this all in, you do all the math work. I'm just going to give you the answer because I'm going to run out of time here. But this is going to come out to be -5 over 8. I believe that is the answer you should get. It's -5 over 8. I'm cheating a little bit. I'm just looking at answers. So if this is wrong, you guys can go blame Brian V. I'm looking at his answer. It looks right, so I'm just going to say that right there. I'm going to throw you under the bus. So if it's wrong, go blame Brian V. Anyone else to throw under the bus who got that same answer? Damn. Anyone else got an answer, though? You're the only one who I've seen so far with the answer. And I think you're right, Brian. No, I think you're right, Brian. I think that's it. -5 over 8. All right. All right, guys. That's it from me today. Hopefully you guys are feeling okay with this. I don't have the homework up yet for the tables one, but I do have a worksheet that I want you guys to do. I'll put that up. I'll put that up later today. I'll put that up before 3 p.m. today, so you guys can take a look at the next assignment. I think that's going to be the last assignment before we start doing review work for your test. Okay, so keep that in mind. If you're behind on homework, get started now. Get caught up now, and then see what you don't know. Start coming into office hours and ask some questions with me. Okay. With that being said, today I have office hours, but I have to leave like 10 minutes early. So come in early if you need to. The answer for B is right there. And secondly, tomorrow I actually have to go to my mom's doctor's appointment. So I will not have office hours tomorrow on Wednesday. So just keep that in mind. If you have questions, come in today. And yes, you can retake the quiz today, Max, as long as you stop by my office hours today from 1 to 2, and I will get that set up for you. All right. Other than that, guys, have a good rest of your day. I'll see you guys later. All right. Have a good rest of your day. So long, guys. Farewell. Bye. Bye, Julia. Bye, Juliet. Have a good day. You too, Emily. Bye, Monica. Have a great day. Bye, Shan. Bye, Leslie. Thank you for stopping by. Bye, Diana. You too. Have a great day. Bye, Jocelyn. I'll see you on Thursday. See you, David. Bye, Ava. Mark, you came in a little late. You all right, man? Everything okay? I didn't get to check in with you. Mark, you there? Showed up kind of late, but hopefully you're okay. I don't know if you're typing right now or you're not even there, but let me know, Mark, if you're all right. Send me an email. Everything's good. Hopefully. All right. I'll catch you later.